In this recording, we continue talking about concave mirrors. What we have defined last time is if we call DO the distance between an object and the mirror, DI the distance separating the image from the mirror, and F the focal length of the mirror, again DO distance from object to mirror, DI distance from image to mirror, and F the focal length, which is, remember, F is R/2, the radius of curvature of the mirror over 2. Then we have this relationship, 1/f is equal to 1/di plus 1/do. Now an interesting example here. What you have a concave mirror, and actually there is no light bulb here, but you see it lit. The setup is such that the image, what we are seeing here as a light bulb, is actually an image, and it looks quite real, but it is an image of a light bulb that's upside down at the bottom of this box. This is the situation. This is where you have object, the blue arrow, and image are equal to each other. And when does that happen? When you place your object at twice the focal length away from the mirror. In that case, DI is equal to DO, and actually you can find it from that equation. 1/di plus 1/do is equal to 1/f. So if DO is twice f, then when we move it to the other side, 1/di is equal to 1/f minus so di is equal to twice f as well. Now, a few questions. The image produced by a concave mirror of a real object is always real, always virtual, or sometimes real and sometimes virtual. Okay, we call here, I think I still have the simulation, so I'm trying to go to it. See, my object is in blue. That's a real image, virtual image. So the answer is sometimes real, sometimes virtual. So where in front of a concave mirror would you place an object so that the image is virtual? Close to the mirror, far from the mirror, either close or far, or not possible. It is close to the mirror. We just saw it in the simulation. When your object is so close, that's when the image is behind the mirror, making it virtual. Now, another equation we are going to add to the fray is what we call the magnification. How much bigger is the image from the object, or how much smaller is it from the object? How do we define that? Definition of magnification, since we are talking of how much bigger something, it's going to be the height of the image over the height of the object. Okay, it can also be shown that this is equal to minus di/do. We are not proving it here geometrically, but it can be shown that it is equal to minus di/do. Now, HI and HO are positive when the object is upright. and they are negative when it is upside down. Now the magnification is going to be positive if we have a real image. What did I say here? I wrote it correctly into the right place, but it is negative for real images and positive for virtual images. Okay, let's work a couple of examples. A candle is placed 6 centimeters in front of a concave mirror with a focal length 2 centimeters. What's the image location? Okay, so 6 centimeters in front of the mirror, that's DO. And it is plus 6 centimeters since it's in front of the mirror. Focal length is 2 centimeters. It is a concave mirror, meaning positive 2 centimeters. If we were told that it is a convex mirror, then it would be a minus 2 centimeters. Now, where's the image position? I solve the equation. 1 over dO plus 1 over di is equal to 1 over f. In this case, 1 over 6 centimeters plus 1 over di is equal to 1 over 2 centimeters. So 1 over di is equal to 1 over 2 centimeters minus 1 over 6 centimeters. Putting in the same denominator, that makes 3 over 6, this one. So 3 minus 1, 2 over 6. Centimeters, and that makes di equal 3 centimeters. And you notice that we obtain a positive 3 centimeters. So what this tells me, my image is 3 centimeters from the mirror. So it's between, like in the image here, between the focal length and the center of the mirror. Now, the question here is not asking me, but what about the magnification? Magnification is minus di over do. So in this case, it's going to be minus 3 centimeters over 6 centimeters. So it is minus 1/2. So the image is going to be half as big, upside down, and 3 centimeters from the mirror. And the real image, half as big, real, and inverted. Okay, we have another question here. A 4 centimeter arrow pointing down is placed in front of a mirror that creates an image with a magnification of -2. What is the size of the image? Okay, so magnification is -2, which is hi over ho. ho is given 4 centimeters. So hi, which is m times ho, which is going to be -2 times 4 centimeters. So it's going to be -8 centimeters. Actually, these are supposed to say centimeters. So this is my answer. Would it be up or down? We have a negative magnification. It tells me it is down. Now, just a summary. For concave mirrors, we have three cases. If the object is inside F, then the image is upright, enlarged, and virtual. If it is between the focal length and the center of the mirror, it's going to be, the image is going to be inverted, enlarged, bigger than the object, and real. If the object is past the center of the mirror, the image is again inverted, reduced, and real. These are the three cases for concave mirrors. One interesting demo that we'll see in class is, some people call it the mirage. So it's a set of two concave mirrors that are placed on top of each other, and you put coins in the bottom or a toy or something, and it's going to look like you can grab the coins there. So you have an actual real image of the coins there, and you try to grab them, but you cannot. Okay, let's see the physics behind that one. This is a simulation that shows it. Okay, you see here, if we place our object here, then light reflected off that object, once it hits this mirror here, it's going to be reflected here and reflected back to form the image here. A real image there, and that's the idea. Now, going back to this simulation here that we played with before, now I have a concave mirror like this. See how we can okay, that makes it better. Okay. See here, they're equal size, bigger, and then inverted. Okay, let's go back, real images, and then inverted. Okay, you see at the focal point, we have an infinite image. That's what you see as really a huge thing there. Okay. What about convex mirrors? Okay, let's look at convex mirrors. Now, look here, no matter where I place my object, my image is going to be behind the mirror, upright, behind the mirror that makes it virtual, and it is upright. Notice it is always smaller than the object, no matter what I do. Now, the principal rays, okay, here, just emphasize how we get the full object by having light being reflected off all parts of the object, and here they are parallel beams, so they look like they would have emerged from the focus behind the mirror. But here's our principal rays. Parallel beam is going to look like it came from the focus. So it's going to come out like it came from the focus. A beam that looks like it's coming from the focus will look like it's coming from the focus. A beam through the center would be reflected from the center. The combination of all three will look like 1, 2, 3. They look like they are emerging from this image here that's behind the mirror. Okay. This is all raised together. Image is always smaller, upright, virtual. Okay. Another example. We have a candle that is placed 6 centimeters in front of a convex mirror with a focal length of -3 centimeters. Notice here they give us the minus sign. Let me go back. Okay, they do not always give the minus sign. The fact that they tell us it's convex mirror, that should tell us that the focal length should be negative. They don't have to tell us that it is negative. But anyway, in this case they did. So we are given DO, 6 centimeters, and F -3 centimeters. We are asked to find DI, I mean. So 1 over DI is 1 over F minus 1 over DO. So it's going to be 1 over -3 centimeters minus 1 over 6 centimeters. So this is 2 over 6. So -2 minus 1 over 6 centimeters. So this is 3. So that gives me DI minus 2 centimeters. So my DI is -2 centimeters, telling me that the minus, it's behind the mirror. So what's the magnification? Magnification is minus DI over DO. So it's going to be -2 centimeters over 6 centimeters. So it is going to be 1/3. If the candle is 9 centimeters high, how tall would the image be? The magnification is also HI over HO. We are told that the magnification is 1/3, and we are given HO. So 1/3 is equal to HI over 9 centimeters. So HI is 9 centimeters over 3, or 3 centimeters, 1/3 as big. Where would you place an object in front of a convex mirror to produce a real image? You can't. All images from a convex mirror are virtual images. A mirror summary: angle of incidence is equal to angle of reflection. That's the basis of a mirror. principal rays, we can use them to determine the position of images. 3 of them that we use, but then we could have used others. Focal length is the radius of the mirror over 2, positive for a concave mirror, negative for a convex mirror. And then this is the relationship between focal length di and do, and this is the magnification equation. One last thing, when we have an object in front of a curved mirror, because curved mirrors are going to magnify objects. If you recall the equation, this is the magnification equation. And the magnification equation depends on where do is and where di is. So actually, if I have an object like this, do for this is different than do from here. What does that mean? That means that we are going to introduce a distortion on our object. So our image is not going to look like it has the same shape as our object. So our sphere here is going to look like this. And then for a convex mirror. And then there is this extra thing, that's the multiple reflections. That's when you are looking sideways at the image. That's why when we look at ourselves in front of curved mirrors, we see distortion. That's due to this.